Okay, after that intro, note you can look at various physical properties, interesting alkenes, lipids, fatty acids, oils, fats, whatnot. In your book, go ahead and read up on those. Our next section is preparation of alkenes. Good news, this is all review, we don't have to worry about it. How did we make alkenes? Dehydrohalogenation of an alkyl halide with strong base. E2 mechanism. Ooh, there's a phrase to memorize. Acid-catalyzed dehydration of an alcohol to form an alkene. And of course we chose sulfuric acid as our alcohol, or TSOH, paratoluene sulfonic acid, such that we did not have a competing nucleophile with the conjugate base of that strong acid. All right, and remember, of course, that if this alcohol is secondary, it'll go via E1, and therefore we're going to have carbocations that could rearrange. So if you didn't want a carbocation rearrangement, when you did your dehydration of the alcohol, you could dehydrate with POCl3 and pyridine, because that dehydrates secondary alcohols via the E2 mechanism. No carbocation, no rearrangements, either yay or boo, depending on how you feel about rearrangements. Okay, so now that we have these alkenes and we've made them, what reactions can we do with them? Well, our first one is hydrohalogenation. Note, hydrohalogenation is the reverse reaction of dehydrohalogenation. Dehydrohalogenation, we started with an alkyl halide and ended up with an alkene. With an elimination reaction, hydrohalogenation, we're going to start with an alkene. We're going to make an alkyl halide through electrophilic addition of HX, a strong acid where we have a chlorine or a bromine. Okay, so here's the reaction. Here's how it works. If you have CH3, CH double bond CH, CH3, the first step is a slow step. Note the pi bond is the weaker bond. The pi bond will act as the nucleophile and will attack the hydrogen. Okay, now, so this pi bond between these two carbon breaks, and one of these carbons will get the hydrogen. So let's say this carbon on the left here got the hydrogen. Well, what happens to the other carbon? Well, if this carbon got the hydrogen, the other carbon is a carbocation. Then we've got Br minus that we also formed in the reaction. Br minus, not the best of nucleophiles, but we've got a nice old carbocation here. So the bromine minus will come in and attack the carbocation and would add the bromine on there. Okay, a few things to watch out for. Number one, we do have a carbocation, so we can get rearrangements. No rearrangements here, because this is a secondary carbocation. If one of these hydrogens moved over, it'd still be secondary, so we're not going to worry about rearrangements with this one, but in the future, you will have to worry about that. The other thing is this was a symmetrical alkene, which means a CH3, CH3, no problems there. But what if we had an unsymmetrical alkene? Which carbon gets the hydrogen? Here we can see that our left carbon got the hydrogen to make this, but if our right carbon got the hydrogen, we'd actually end up with the same thing. It did not matter. However, there is a nice rule named after Markovnikov. Markovnikov's rule says in addition of HX to an unsymmetrical alkene, the hydrogen atom bonds to the least substituted carbon. The hydrogen goes on the carbon that already has more hydrogens on it. That's the way I remember it. So if you've got an alkene, going to add a hydrogen to it, the hydrogen goes onto the carbon that has more hydrogens on it to begin with. Now, Markovnikov didn't know this at the time, but the reason is if the hydrogen goes to the carbon of the alkene with more hydrogens already on it, that makes the more stable carbocation. And we will see that in the next couple of examples. So, let's look right here. Here we have CH3CHCH2. Note, methyl on this carbon, just 2 hydrogens on the other carbon of the alkene. The double bond attacks the hydrogen of HCl. Which carbon will get the hydrogen? Well, Markovnikov says the carbon with more hydrogens gets a hydrogen. This left carbon only has 1 hydrogen on it. The right carbon has 2 hydrogens on it. So the carbon with 2 hydrogens gets that other hydrogen to make this a CH3. This becomes a CH3, and this is now a secondary carbocation. Note that if this carbon on the left got the hydrogen, then we would have had a primary carbocation. Primary carbocation is not stable, so that is why Markovnikov's rule is what it is. The carbon with more hydrogens gets the hydrogen, and that generates the more stable carbocation. Then the chloride that was also generated could come in and attack that carbocation, and we get the chlorine on that carbon. It ends up being the middle carbon in this 3-carbon chain that we started with. Note, Markovnikov's rule is when you start with an alkene, where does the hydrogen go? Zaitsev's rule, when you start with alkyl halide or an alcohol and you form an alkene, where does the double bond go? Alright, so let's look at a nice example here. Here we have this 1-methyl cyclohexene, and we're going to add HCl. Well, we say, okay, I've got a HCl, strong acid, I've got an alkene. This is going to add HCl across the double bond. That's our terminology. We add HCl across the double bond because the H goes on one carbon, the chlorine goes on the other carbon of the double bond, so it's across. So the question is, which carbon is going to get the chlorine? Where's the chlorine going to end up? Well, we know that there are no hydrogens on this top carbon. There's 1 hydrogen on the bottom carbon. The carbon with more hydrogens gets the hydrogen, which means the top carbon of this alkene gets the chlorine. Chlorine's going to go there. All right, well, let's spice it up a little bit, shall we? What happens with this molecule? Okay, we've got this tert-butyl group and this CH double bond CH2. We're going to add HBr. Now, without looking further, one might say, okay, the hydrogen goes on this carbon, therefore the bromine will go on this carbon. Well, that makes sense in a nice world where unicorns scatter fairy dust all over the place and everybody eats jelly beans and doesn't gain weight. However, that's not reality, because we're going to find out the bromine's actually going to this carbon over here. How's that possible? Well, let's look. Markovnikov's rule says that when this double bond attacks this hydrogen, that the hydrogen goes on the carbon with more hydrogens. This has 2, just 1 here. The hydrogen's going to go on this carbon that contain more hydrogens, making that a CH3 and making this a carbocation. And that's what we have here, a CH3 carbocation. Note that's a secondary carbocation. Note that, whoa, secondary carbocation, is there a way to make it tertiary? Sure enough, if this CH3 moved over to here, then the carbocation would move here, and we get this tertiary carbocation, which is more stable. So then the bromine is going to end up on this carbon here. The bromide ion will attack this carbocation, and we end up with this product over here. So watch out for that. Watch out for these rearrangements, because this does go through a carbocation mechanism. So anytime a rearrangement can occur, it will occur. And at this point, everyone says the same thing. Well, that's wonderful, but what about stereochemistry? Well, I'm glad you asked. Let's look at that. Here we have this molecule here. Here's our carbon-carbon double bond, and we're going to add HCl to it. I think Markovnikov will tell us that the H will go on this carbon, because it contains 2 hydrogens, which means the chlorine is going to end up on this carbon over here. Note that this carbon would be the carbocation, and it's already tertiary, so we don't have to worry about rearrangements, because when this forms a carbocation, it'll be tertiary already. So chlorine will go there, but note, if we make this product, this carbon has a chlorine, a methyl, an ethyl, and a propyl group. We've got a chiral carbon here. Was it chiral to begin with? No. which means we don't have any optical activity on our reactant side. None of these two are optically active, which means our product cannot be optically active, but we generated a chiral carbon, which means if we generated a chiral carbon, we've got one of the enantiomers. If we can't have optical activity, we need the other enantiomer. We generate a racemic mixture of these two enantiomers. And the way this happens is, note that when the double bond attacks this hydrogen, the hydrogen goes on this carbon, and we generate a carbocation. If we say the hydrogen came onto this carbon on this side, the hydrogen was added from the top side. Note the chloride could add from the top side the same side as the hydrogen. We call that syn addition. Or the chloride could have attacked a carbocation from the opposite side the hydrogen came on. We call that anti-addition. Now, since this is a single bond that we made, it used to be the double bond, but it's a single bond when we generate the carbocation here. This bond can rotate, so syn addition versus anti-addition doesn't matter too much. With this thing, the real deal is the chlorine could come in from this side, which would push these three groups down, or it could come in from the other side and push those three groups up, making the two enantiomers. However, if you have a ring where you cannot get bond rotation, then syn and anti are, well, we can use those terms a little bit better because we can see things will come in on one side and something will definitely come in from the other side. So let's look at this molecule right here. Here's our alkene at HCl. We can see that both the carbons of the alkene are the same, so it does not matter which carbon gets the hydrogen. So let's put the carbon that gets hydrogen, let's say it's this top carbon here gets a hydrogen. And let's just say, we could have picked any direction, but let's just say that this hydrogen comes in from the back. So the hydrogen's on the back and it comes in and attacks this carbon. And so this methyl group is now coming out towards us, and the hydrogen is back there. Note, this carbon over here, the other carbon of the double bond, becomes a carbocation. Geometry of carbocations, they are trigonal planar. So we have this trigonal planar carbon right here. So then the question is, which side could the chlorine come in on? Well, it's a flat trigonal planar carbocation. The chloride could come in from the top side, and we generate this guy right here. Note that is anti-addition because the hydrogen came in from the back side and the chlorine comes in from the top side, anti-addition, to get this. Or the chloride can come in from the back side, can come in from my desk here and go up this way and push this H3 out, and we get this. And this is the syn addition product. But if we look closely at this anti and syn addition products here, we see these are not enantiomers. Because, oh, look at this bottom carbon here. We switched the two groups on the bottom carbon, but the methyl's still coming out on the top carbon. Methyl's coming out, hydrogen's coming back, so the top carbon is the same. Question, if these two are not enantiomers, but they're not the same thing because we've switched two groups on only one carbon, what is their relationship? That's right, these two are diastereomers of each other. Well, if they're diastereomers, then that means that we still have optical activity because one diastereomer has a different rotation, a different alpha than the other diastereomers. So these are not enantiomers. So we do need the other enantiomers of these two. And you can draw the enantiomer of this diastereomer by switching both groups to get this guy over here. And the enantiomer of this one is switched both groups to get this one. Note the enantiomers come about. Here we said the hydrogen came in from the bottom side. Here, what if the hydrogen came in from the top side? And we got syn and anti-addition. And so we generate all four of these products. Note, because these two carbons are the same, to get all four products, the two sets of enantiomers here, I just said, what if the hydrogen came in from the back side? What if it came in from the top side? You could have done the same thing using the bottom carbon. What if the hydrogen came in from the bottom top side? What if it came in from the bottom and back side? And you would have generated all four of these exact same stereoisomers. Okay. So, note that reaction there, the hydrohalogenation, was the opposite of our dehydrohalogenation. Dehydrohalogenation of an alcohol made the alkene, or excuse me, dehydrohalogenation of the alkyl halide made the alkene. Hydrohalogenation of the alkene makes the alkyl halide. The other way we made alkenes was a dehydration reaction. You are probably not shocked to find out that we have the opposite of a dehydration reaction, a hydration reaction, where we start with the alkene, add water across the double bond, and make the alcohol. Note, if you just take an alkene and throw it in water, you've got alkene floating on water. No reaction is going to occur. You need a catalyst. What catalyst does one recommend? I recommend an acid catalyst, and I recommend H2SO4. Why do you want to use H2SO4 as our acid catalyst? Because then it can catalyze a reaction. The conjugate base is HSO4-, which cannot be a nucleophile, so you don't have to worry about any substitutions or anything crazy going on in there. So if you take an alkene, throw it into water, nothing will happen. Add acid catalyst, you will get your alcohol. All right, this follows Markovnikov's rule. The first thing that's going to happen is the alkene will attack the hydrogen of your catalyst, and the hydrogen will go on the carbon that has more hydrogens on it. That will generate a carbocation, so we will have syn and anti-addition, and rearrangements will be possible. So let's look at the mechanism of this reaction. Here I'm just using H3O+. Usually it's going to be sulfuric acid or paratoluene sulfonic acid. So the double bond attacks this hydrogen. The hydrogen goes on one of these two carbons. They're the same, so we don't worry about it. Hydrogen, let's say, went on the top carbon. The bottom carbon's a carbocation. H2O now attacks that carbocation. And so we've got an H2O note. That's going to give us, tough to see here, H2O, a hydrogen here, positive charge on that oxygen. And anytime our product has an oxygen with hydrogens on it and positive charge, a dehydration reaction will happen. We've got to get our acid back, so another water molecule will come in, snag that hydrogen. Those two electrons will go on that oxygen, and we'll end up with the OH on here and our acid catalyst back again. All right. Something nice with these reactions is that, what is the pKa of water? Well, pKa of water is 15.7. Alcohols have pKa of 16 to 19, so often anytime water will do a reaction, an alcohol can do the reaction too. If you have a carbon-carbon double bond and you have an alcohol, it turns out you throw in some acid. The one carbon here, the double bond will attack the hydrogen. The hydrogen will go on the carbon with more hydrogens, Markovnikov's rule, leaving this carbocation here. And when we have this carbocation, then the oxygen of the alcohol can attack that carbon, and we will end up with this ether from this acid catalyzed reaction.